All right, let's talk about 7.1 trigonometric identities. Let's talk about the Pythagorean identities first. And it says, given theta, some angle that is a real number, so any real number you feel like, cosine squared theta plus sine squared theta equals 1. And you've seen this before. Of course, we derived it way back in chapter 5 when we were talking about the unit circle the first time. But there are actually two more of them. The first one is 1 plus cotangent squared theta equals cosecant squared theta, and then the other one is 1 plus tangent squared theta equals secant squared theta. And then example 1 here says, derive the last two of the above identities. So I'm going to start with this one here. And we're just going to come right up here and do it. So what I'm going to do is I'm going to start with the one that we know. We know this guy right here. So I'm going to start with him, and I'm going to write it the other way. I'm going to write sine squared theta plus cosine squared theta equals 1. And we know that we're allowed to do that. Of course, this being the y part, this being the x part, and this being 1 squared, the unit circle has radius 1. This is just the Pythagorean theorem, is where all this comes from. But we're going to then take this and just simply divide each term by sine squared theta. Sine squared theta divided by sine squared theta divided by sine squared theta. And if you're confused as to why we're allowed to just divide both of these terms, think about taking just these two up here and multiplying by 1 over sine squared theta. When you distribute it in, you're going to get this. And then you divide the other side by sine squared theta. And then watch what happens. Sine squared divided by sine squared, anything divided by itself is 1. This plus is this plus. And then we know that cosine over sine is cotangent. So if cosine over sine is cotangent, then cosine squared over sine squared is cotangent squared. Equals, and if 1 over sine is cosecant, then 1 over sine squared is cosecant squared. So we've derived that identity that way. So go ahead and write that down, because I'm just going to reuse this space to do the other one. So let's go ahead and redo the other one as well. But this time, let's instead talk about this guy right here. So I'm going to start with the exact same thing, but this time we're going to derive this guy. And you can probably guess how we're going to do this. Last time I divided everything by sine squared. This time I'm going to divide everything by cosine squared. And watch what happens. Cosine squared theta divided there, divide the other side by cosine squared theta. Watch what happens. We know sine squared theta over cosine squared theta is tangent squared theta. We know that. Plus anything divided by itself is 1 equals, and then 1 over cosine is secant. So 1 over cosine squared is secant squared theta. Of course, if you want it exactly like this, then you're more than welcome to just rewrite everything over here like this, and there you go. So we know that secant squared theta is 1 plus tangent squared theta. And these are incredibly useful to remember. And you sometimes see them in their other forms, which are where you've solved for the other variable. So sometimes you can see this guy here as cotangent squared. So cotangent squared theta equals, you just subtract the 1 over. Cosecant squared theta minus 1. And sometimes you see this guy as solve for secant squared. Secant squared theta equals, or rather, it's already solved for secant squared. Sometimes you see this guy here solved for tangent squared, so it's just tangent squared theta equals secant squared theta minus 1. Sometimes we just use that. And of course, there's two different forms for this one up here. You can either solve for cosine squared and get cosine squared equals 1 minus sine squared, or solve for sine squared and get 1 minus cosine squared. But really, if you just know this first one, you can derive all of the rest of these just by either dividing everything by cosine squared or dividing everything by sine squared. You'll get everything, and then it's just as simple as subtracting some stuff to the other side. It's no big deal there. So there's just a whole bunch of identities here. So these next couple definitions, the first ones are the even and odd identities, which we've already written down before. But the cosine and its reciprocal function secant are both even. So that we have that the cosine of a negative input is the same thing as the cosine of a positive input. Same thing for secant, because secant is just 1 over cosine, so of course it behaves the same way. All the rest of them are odd, which means the sign of a negative output is the same thing as negative sign of a positive output. Think of it like you can pull the negative sign out for odd, and for even, it just dies in a fire. It just goes away. All right, it evaporates if you want to use the same letter. Write those down. Get those down in your notes. And the same thing for reciprocal identities. We've went over those before as well. We've already practiced them a bunch. But sine is 1 over cosecant. Cosecant is 1 over sine. Cosine is 1 over secant. Secant is 1 over cosine. Tangent is 1 over cotangent. And cotangent is 1 over tangent. Write those down. Get them down in your notes. Commit them to memory. It's incredibly useful to know these things. But that's all that there is to say with that. So go ahead and pause the video, because I'm just going to continue onward. Get these down. We've already done a bunch of practice with it. We got a bunch more practice to do with it. And that's just because it's important that we know it. So get those down, and we're going to continue. And then the last couple little identities here are called the quotient identities, because they have to do with a quotient of 2 different things. And it's literally the definition of tangent and cotangent, which we've went over multiple times as well. So tangent theta is sine over cosine, and cotangent is cosine over sine. Awesome. So I want to do a few proofs here. Now, there aren't a lot of proofs in our practice, and you'll probably be very happy about that. But I do want to show you all the power of some of these identities. And I want to impress upon you that these are sort of the things that we're going to be doing a lot of in this chapter, in these videos, is I want to show you that you can turn trig things into other trig things, things being expressions, trig expressions into other trig expressions, using these identities that we've already written. You pretty much only need those. There aren't a lot more identities that we're going to get, but there are some more formula that we're about to go through for sum and difference and double angle and whatnot. And they're going to come in very handy in Cal 1, but especially in Cal 2 when we get to it. But we're going to do some proofs here. And I know that proofs are probably something you're not particularly interested in, especially after geometry. That probably brings back some awful memories. But honestly, I find these things to be very fun. They are little puzzles that I enjoy. So here's the deal with the proof. You have a roadmap here that says we're going to start on this side, the left-hand side, and get to the right-hand side. So we know where we're going. So as long as I can use the above identities that you've already written down on your paper, and if you haven't, you should really do that. If we can get from the left-hand side to the right-hand side, or vice versa, we can start with either side we want to, then we're good to go. So we know in a proof where we're supposed to end. So if we can just get from the beginning to the end, we're good. So we're going to do a proof here. And this proof is pretty simple. So we're going to start the proof however you want to start the proof. But you have to say proof to start the proof. So some people like to write proof, and then put a little period after it, and then they're going to write their period, and they're going to write their proof rather, and they're going to put a box at the end. Some people do proofs like that. I personally get a little bit more fancy. I do this little fancy proof thing like this. That's just how I do it. And then we're going to say we need to start with one side and get to the other side. And which side looks more complicated? Well, this side has a square in it, so we're going to start with this side. That's just me. You're welcome to start over here, and I'll show you how that proof would go in just a second, and just get back to the left-hand side. But you assume one side is true, and you get to the other side using trig, and you explain to me how you do it. So, we'll say this, given sine x plus cosine x, all squared, right? We will expand. So we're just going to expand this thing. So expand to get. So we will expand to get. And now we're just going to expand this. So we're going to do sine x, and I'm going to show the reader what it is we're doing. So sine x plus cosine x, all squared, that equals, we're just going to multiply this times itself. So if you want to write out every single step, that's sine x plus cosine x times sine x plus cosine x, like that. And then when you expand this out, we're just going to FOIL it. Sine x times sine x is sine x, sine squared x. Then you're going to get, look, a sine x times a cosine x, so sine x cosine x, and a cosine x times a sine x. So another sine x, cosine x. So there's two of them. There's one of them here, sine times cosine, and here there's a sine times cosine. So there's two of those. So it's plus 2 sine x cosine x, which we'll later learn an identity for that one as well, plus, and then we multiply the last terms, cosine times cosine is cosine squared. Okay, period. We're done. That was a sentence. We will expand to get, did some math, that's the end of the sentence, put a period. Now we say another line. We say, noting that sine squared x plus 2 sine x cosine x plus cosine squared x can equal, I'm just going to, we note, we look at this and we see what can we simplify and where are we trying to get? Well, in the answer we know that there's going to be a 2 sine x cosine x and it's right there. So we don't have to worry about that. So don't worry about it. Don't look at it anymore. We know that that's part of the answer. So what's left? Sine squared plus cosine squared. And that should look really familiar. Look back at your notes and tell me what that is. And what do we want? We want a 1. We have a sine squared plus cosine squared. And notice I'm saying sine squared plus cosine squared. I'm not saying the variable, but you always have to put the variable. You don't get to write sine squared plus cosine squared. That's meaningless. That's like writing the square root of and then not writing anything inside of it. It doesn't make any sense. But when you say it, you can shortcut it. So we have the sine squared plus cosine squared x. So I say, note that this term can be rewritten as, and I'm just going to write the sine squared plus cosine squared first, because we want the 1 first. And the reason that I think that a lot of people that come and take trigonometry end up not liking the class, this part of the class especially, is because you actually have to think. And I don't mean this as an insult, but you guys haven't really done a lot of thinking in your mathematical careers. Noting that this equals this, comma, since sine squared x plus cosine squared x equals 1, we have, and then you tell me this. You have that sine squared, you just told me what it was. So instead of writing sine squared x plus cosine squared x like this, we're just going to write 1 plus 2 sine x cosine x, which is what we wanted. So we're done. So you put a little box. And that was the end of a sentence, so you put a period. And that is the technical correct way to do the entire proof. So you tell me what you were given, then you give me the step-by-step. And I should be able to read what you wrote in paragraph form and deduce everything that you're doing. And this is the kind of stuff that we're going to be doing more and more as you get further and further along into my classes, is critical thinking and putting down on paper exactly why it is that what you're doing. Though I will tell you that for trigonometry, we can actually rewind quite a bit, and I'll show you how we can do proofs in this class. And it's really just the work is all I need. So that would have been the correct way to write it, and you should absolutely do it that way. That's a great practice to get into. But you can write it like this. Well, we have sine x plus cosine x all squared, and that just equals sine x plus cosine x times sine x plus cosine x, which just equals sine squared x plus 2 sine x cosine x plus cosine squared x. And then I'm going to come back over here. This just equals sine squared x plus cosine squared x in parentheses plus 2 sine x cosine x. The parentheses aren't necessary, but they do draw the reader's attention to it. It's just a good practice. And then we just say that that's 1 plus 2 sine x cosine x. Done. That's the proof. Just the work. And this is simple enough that you don't really need to explain what it is that you're doing. But if you write down what you're doing and why you're doing it, you're going to have a much better idea of what it is that you did. And you're going to have a much better idea of why it is that what you did works. More importantly, you're going to have a much better idea of why it is what you're trying to do isn't working if you're actually writing down your logic and you write down something that doesn't make any sense. You'll be like, well, okay, maybe this is the wrong way to be going on these. And like I promised, I was going to tell you all that you could have done it the other way. You could have started with the right-hand side and went to the left-hand side. Just read the proof backwards. So you would have had to have noted that 1 is just sine squared plus cosine squared. And then you would have multiplied it together like this and noticed that and you could have factored this form here into this and then rewrote it like this and been done. If you wanted to do it that way. Up to you. So in this next example, we're asked to prove that 1 minus cosine squared theta equals 1 plus cotangent squared theta equals 1. Obviously, the left-hand side is much more complicated. You can start with 1. Good luck getting anything out of that. So there's a whole bunch of ways that you can do this. Your mind may see this and say, okay, I just want to FOIL that out. Because you've been trained to look at that and FOIL it out. And you may get something useful out of that. It's not the way that I would do the proof, but I'm going to start my proof. You can write the word proof if you want to, however you want to start it. Let's see what happens. Let's just see. Let's play around with this and see what happens. So you want to FOIL this out. You say that's probably the strategy to do it. And it's definitely not the simplest strategy to do it, but maybe you don't know that. So cotangent squared theta. And you don't get to say that it equals 1 yet. This is where you're going to. Ignore this for now. You have to fill in all the blanks, and then eventually at the end of the proof, you get to say that it equals 1. But this part right here is the part that you're actually trying to show me. That part right there is the answer to the proof. All the math you've got to do in between it. So don't say it equals 1 immediately. You don't get to say that. You choose one side. You do the math to get to the other side. Proofs are saying this does equal this. Show me how. So if you immediately jump to the conclusion, that doesn't show me anything. If I ask you, explain to me how the sky is blue, and you say, well, it's blue, that doesn't answer anything. So don't be doing that. Let's just go ahead and expand all this out. Let's multiply everything out. So 1 times 1 is 1. 1 times cotangent squared is plus cotangent squared theta. I'm just expanding these plus, or minus rather, minus cotangent squared times 1 is minus, cosine squared rather, is minus cosine squared theta. And then we get a minus a positive is a minus, and then cosine squared times cotangent squared. And that might turn into something nice. Cosine squared theta times cotangent squared theta. That might turn into something. So we know that. And I'm going to come all the way over here because I need the space. So let's write everything in terms of sines and cosines. That's usually, if you get lost in the middle of all of this, writing everything using the reciprocal and quotient identities in terms of sines and cosines is usually a good strategy. So let's just try that. So that's 1 plus. So I know that cotangent squared, cotangent is cosine squared theta over sine squared theta. Okay, minus, and then we're going to write our cosine squared theta. Well, that's already written in terms of sine and cosine, so we just copy it. Minus cosine squared theta, which is already written in terms of cosine squared theta. And then cotangent is, again, cosine squared theta over sine squared theta. And, oh man, we're in a big mess here. Look at this. This is awful. This is the worst. I mean, what do? Do we get a common denominator for everything? We've got a sine squared over here and a sine squared over here. Does putting sine squareds in each one of these terms, does that necessarily help us? I don't know. Let's just try that. Let's just see. I want everything written in terms of sine squared so I can put it all together. Well, I know that in the end, let's keep track of what we're wanting. We're going to want a 1, and we've got a 1 right here, which means that all of this must cancel somehow. So how do we get all of this here to cancel? What can we do? Well, maybe if we just put everything together on top, it'll all cancel and it'll just work out for us. So let's get a common denominator for all of this stuff. Let's leave the 1 alone, because I know that we want the 1 in the end. That's what I'm trying to say. So if we want the 1 in the end, let's just leave that alone. So 1 plus, I want everything over sine squared. I want a common denominator. So cosine squared over sine squared theta already has the common denominator minus, We need a sine squared theta here, so we have to multiply top and bottom by sine squared theta. So we'll get the cosine squared theta times sine squared theta over sine squared theta. Okay, we're just trying to get a sine squared theta on the bottom. Of course, those will just cancel. You'll be back to where you want. That works. Minus, and then I'm just going to multiply these two things together. So this is cosine to the fourth theta over sine squared theta. Cool. And then maybe in the next step, if we write all of this as one giant fraction, it'll all make sense to us. Let's try it. So this is cosine squared theta minus cosine squared theta sine squared theta minus cosine to the fourth theta all over sine squared theta. Okay. Is this looking any better? Is this looking any closer to all of this stuff inside these brackets here just collapsing on you? Are you seeing a pattern here? Is there anything that we can do that we can factor out maybe that's going to be useful to us? And I am seeing some stuff that we might be able to do here that might get everything to cancel down. So yeah, we might be able to do something with this. So let's scroll down. But we don't have a lot more space. But let's see what we can do with this. So let's scroll down and see what we can do with this. So this is 1 plus. I'm going to factor out the cosine squared, a cosine squared from the top term. So this is going to be cosine squared theta times 1. If you factor out cosine squared from cosine squared, you get 1. Minus, we pulled out the cosine squared, so there's just a sine squared left. Okay, minus, we pulled a cosine squared out of a cosine to the fourth, so there's a cosine squared left here. Okay, and there's a very easy identity here that we can do that'll immediately solve this for us. But there's a bunch of different ways to go about this problem from here. So you can start noticing some patterns. 1 minus sine squared theta, that is just cosine squared theta. I don't have any more space. That is just cosine squared theta. And then, of course, cosine squared theta minus itself is 0. 0 times this is 0. Over this is 0. 1 plus 0 is 1. You're done with the proof, if you want to do it that way. Another way to notice this would be, notice this part right here. Sine squared theta minus cosine squared theta is 1. 1 minus 1 is 0. Times this is 0. All of that turns into 0, and you're done. Also fine. Another way to do that. You may even be able to turn this cosine squared into 1 minus sine squared, multiply it back in, and everything's going to cancel. There's a lot of ways to skin this cat and finish this problem off. The easiest way to do it, I would say, would just be the first one that I said. Turn that into cosine squared, and you get cosine squared minus cosine squared on the top. That's 0. Times cosine squared times this cosine squared is 0. 0 over sine squared is, of course, 0. 1 plus 0 is 1. You're done with the proof. And you're sitting there thinking, oh my God, this is so much work. How am I ever going to learn this? What's going on here? This is ridiculous. And the whole reason that I did this was a ridiculous way to do the problem, but it did get the problem done. But there's a much simpler way to do this. And if you put some critical thinking into it at first, not only do you want to try to do this, so let's back up, not only do you want to try to do this problem, you also want to try to do these problems in a way that isn't going to give you some sort of aneurysm midway through. So let's scroll back up to right here and finish this problem off. So let's start right back here again, all the way back at the beginning, and let's do something really simple. Look back for just a moment at your paper and recall that sine squared theta plus cosine sine squared theta plus cosine squared theta equals 1. Which means if you solve for sine squared, that sine squared theta is 1 minus cosine squared theta. 1 minus cosine squared theta. You mean that thing right there. So this thing right here, based on what I just wrote, this thing right here is just sine squared theta. This is just sine squared. Okay? Now, at the same time, go ahead and look back at your original stuff as well and see if you can't find an identity for 1 plus cotangent squared theta. What is that? Well, that was the one where you divided everything by sine, right? So this is just cosecant squared theta is all that is. Which means that this whole thing is just sine squared theta times cosecant squared theta. Just using two little Pythagorean identities. Well, now you just have one reciprocal identity, and that's about it. You have sine squared theta. Remember, cosecant is 1 over sine, but it's squared, so square it. And look, cancels. It's 1. You're done with the proof. That's the whole proof. So I went through all that extra work just to show you that there's a lot of ways to do this. But following your gut on these isn't always the best idea. Look at every single term in here and see if there's any powerful things. The first thing that I notice, having done a lot of trig, is that there are squares on my trigonometric functions. The moment I see a square, I think Pythagorean stuff. This is Pythagorean stuff. So look at the Pythagorean stuff. You'll notice that even in that last version, which I hope you wrote down and finished the proof for, but even in that last version, you'll notice that we did end up having to use this version, or a version like this, in the end anyway. There's no getting out of it. But if you just use it up front, it's a 3-step proof instead of taking 5 pages. So put some critical thought into this and try to minimize the amount of work you can. Can you get to something in 2 steps instead of 17? Well, then 2 steps was the better solution. If you put just a little bit more thought into it. There's a lot of ways to skin this cat, but this is the easiest one that I have found. And maybe you can find another way to do this problem. Who knows? Give it a shot. So in this next one, I invite you to take a look at it. You have cosine squared beta minus tangent squared beta equals 2 minus sine squared beta minus secant squared beta. I want you to prove that. So pause the video and give it a shot and think to yourself for just a moment. What is it exactly that you see in this problem that makes you think a certain thing from that list that we wrote down earlier? We wrote down reciprocal and Pythagorean and quotient identities and even odd identities, and you've got cofunction identities from back earlier in the year as well. Which one of those is going to get you from one side to another? Do you start with the left-hand side? Do you start with the right-hand side? Which one looks harder to you? Which one looks more complicated? What do you turn into other things? Start with one side, get to the other side. See if you can do this yourself before I show you the answer to it. You're going to get a lot more out of it that way, because you're going to have to do these at some point by yourself anyway. It's going to be way up into calculus, calculus 2, and suddenly you're going to need to know how to do these, and if you didn't put any practice into it, well, that's on you. So pause the video and give it a shot. So we're going to go ahead and do this. So I, myself, am going to start with the left-hand side. I don't think that it's any harder. I see this 2 over here, though, and I think I don't want to have to try to turn a number, like 2, into other numbers or split it apart and do things. I know that turning numbers into trig functions is much harder than turning trig functions into numbers. So I want to start with the left-hand side. So I'm going to start my proof with a proof box. That's just how I do it. And then I'm going to write it. I'm going to say cosine squared beta. And look, if you don't want to write betas, just write x's. Just make sure to change everything, whatever you want to do. But I'm going to write betas. Cosine squared beta minus tangent squared beta. Okay. And I'm going to look at each one of these and I'm going to say, well, I see squares there. And when I see things squared, I think Pythagorean stuff. So look back at your list of Pythagorean stuff and see if there's anything that we can turn these into. And I know in the end, I need 2's, which is just 2 1's. I need a sine squared term, and I need a secant squared term. So can I perhaps write this cosine squared in terms of sine squared? Can I perhaps write this tangent squared in terms of secant squared? Do you have anything there in your notes that might help you with that? Take yourself a moment and go look in your notes and see if you can't find that. Maybe it'll click for you. So I know that cosine squared, right here, cosine squared, that's just 1 minus sine squared. 1 minus sine squared what? Which is why I don't always say the argument. 1 minus sine squared of whatever was plugged in, beta in this case. So I'm going to write that. That's 1 minus sine squared beta. Like that. That's the first term. Minus, and then the second term. What is tangent squared beta equal to? Well, it's equal to secant squared beta minus 1. That's one of those alternate forms that we solved for. You have that tangent squared plus 1 is secant squared. So if you subtract 1 from each side, you get that. Well, let's just follow our nose on the rest of this. So that's 1 minus sine squared beta. And then I'm going to distribute in this negative sign. So that's going to be minus secant squared beta minus a minus 1 is plus 1. The only thing left to do is notice we've got 1 plus 1. That's 2. Minus sine squared beta minus secant squared beta. And look, that's what we wanted. So we're done. I know we're done because we just got what we wanted. That's it. We made a little notice. Now, if you chose the right-hand side and we're trying to get back, you would have to break up 2 as 1 plus 1. And then group things like this in order to get back here. That would have been harder, but you could have done it. It'll always work both ways. And it'll just be backwards from the other way that you did it. And that's the last of the examples for this video, and it's very close to the end of the video. Proofs aren't something that I'm super focused on in trigonometry. The gist of the video, if you get this, is that using these identities, we can make two different trig expressions, and we can show that they are the same thing. Notice that the left-hand side and the right-hand side of this, they don't even use the same functions. This one has a 2 in it. So the sides look very different, but they are the same thing. In fact, if you don't believe me, you can use x's instead of betas. Go on Desmos. Graph both sides of this. They will look exactly the same. So keep that in mind. You can have trigonometric functions that look very different. Whole expressions, in fact, that look very different, but do the same thing. Because of all of these identities, and because of all of the geometry behind this subject, you can have things that look very different. And I keep saying that because you should have absolutely written it down by now. So I'll say it one more time. Please put this down in your notes. Trigonometric expressions and functions can look very different from one another, but be the same because of identities. That's all for now. I'll see you back in 7-2.